molecular orbital theory, which I have to say very slowly or else I'm going to get sideways when I say it. Molecular MO theory, molecular orbital theory. So recall from chapter 1, or from principles 2, I guess, that atomic orbitals combine to make molecular orbitals. And when two atomic orbitals, so here's an example of an atomic orbital and an atomic orbital, they combine, they mix, they make molecular orbitals, right? So if we're talking about something coming from an unhybridized p orbital, right? Can you see that? And here's an unhybridized p orbital, right? If they mix, they're going to make side-to-side overlap pi orbitals. Now this is called pi, and this is called pi star, because this one is bonding, and this is anti-bonding. Okay? So, remember that? All right, so now recall that the pi bonding, I already said that, pi bonding and anti-bonding molecules for ethylene, which is more stable? Which is more stable? Well, of course the bonding is more stable, and we predicted bond order. We predicted bond order by counting the number of electrons in bonding and subtracting the ones from anti-bonding and such. Remember doing that? Okay. So what is a node? You see a node right here? A node is a location where electrons, how do you spell electrons? Electrons do not go. Okay? There's no electrons here in a node. It's, I think the classic definition of that, or the official definition is it's a volume in which the probability of an electron, or location in which the probability of an electron is zero. The probability of finding an electron in that volume is zero. Okay, that was nice, wasn't it? So that's what a node is, and with an anti-bonding orbital, you'll have a node. Okay, and then the bonding, these overlap very nicely, and it turns out that's stable and low energy. All right, so if we take butadiene, we've got 6 carbon atoms. Can you see 1, 2, 3, 4, right? Did I say 6? 4 carbon atoms for butadiene. 1, 2, 3, 4. And these are all trigonoplanar. They're all flat. Okay? And there's an unhybridized p orbital here in this axis, and another unhybridized p orbital on that axis. Here's another one, and here's another one, and they're depicted over here a little more realistically by, and over here, a little more realistically by the volumes that the electrons are likely to reside in. Okay, and so if you take 4 of those unhybridized p orbitals, 4 unhybridized p orbitals, and you mix them, you're going to get 4 molecular orbitals. Okay, and in the lowest energy molecular orbital, all of the phases are parallel, right? So you've got, phase up, phase up, phase up, phase up, phase down, 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 right? Phase up, phase up, phase up, phase up, phase down, 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 down. These are not charges, by the way. This plus and minus would make more sense if we looked at the actual wave function of the orbital. But for now, just consider it like up or down, or plus or minus, or black or white, or whatever. Okay, positive, negative. So that said, the lowest energy molecular orbital has all of the phases aligned, and the second lowest has one node. Right, there's my one node for the second lowest, the second most stable molecular orbital. Here's another molecular orbital. Here's another molecular orbital, right? Molecular orbital. These are all molecular orbitals. So when we have 2 nodes, that means we've got 2 areas where no electrons exist. Okay, so these become higher and higher in energy, and then 3 nodes is where none of them are in line. None of them are in phase. All right, so with butadiene, you've got 4 electrons in the 2p orbitals, 1 in each of these here, right? And so they go into these 4 molecular orbitals. I'm sorry, these 2 molecular orbitals. Okay. So the 4 pi electrons in butadiene will occupy the lowest energy molecular orbitals, as we showed in the previous slide. How does this affect stability? Well, it increases its stability, right? Now watch this. If you look at the lowest, 2 of them, 2 of the electrons extend over the entire molecule, and they show up some in here, right? Can you see that? Because there's no node there. So there is some probability of an electron being in this area. All right? Now in the second molecular orbital, this is the lowest energy molecular orbital, and this is the second lowest. Okay? Here, there's no nodes, so there's some electron presence here. In this molecular orbital, the 2 electrons that occupy this one will not show up in this node, right? That's the node. All right, so that means you've got some double bond character here, because this is a pi, right? This is a pi orbital. So you have some double bond character between carbons. Let's see, carbon 1, carbon 2, carbon 3, and carbon 4. All right. Now, molecular orbital theory also explains why the carbon-carbon single bond is shorter and stronger than a typical carbon-carbon single bond. I promised in section 17.2 that there'd be more to it. First of all, this carbon is sp2 hybridized. These 2 are sp2 hybridized. So this single bond right here is made up of end-to-end overlap. It's a sigma bond. It's made of end-to-end overlap between 2 orbitals that have more s character, right? Because they're sp2, in contrast to the typical sp3 single bonds, right? So they've got more s character. They're 33% s character. It's going to be shorter, but they're also shorter because they've got some double bond character. All right, and I think that's all we're going to say about molecular orbital theory.